The dielectric mirror has a stack of several pairs of quarter-wave thick layers. These mirrors are also called Bragg mirrors or distributed Bragg reflectors. The reflectors operate around some center wavelength, and their bandwidth depends on refractive index difference of the layers. As we remember from the previous lecture, if we add optical thickness equal to half a wavelength, the optical reflection at the center wavelength does not change. Let's investigate if some other wavelengths fulfill this condition in our structure. The thickness dl is quarter wave thick. Now we are seeking wavelengths lambda m so that the optical thickness of the original quarter wave thick layer is half a wavelength thicker. First the quarter wave thickness and then half a wavelength thick layer more. And actually we can add multiples of half the wavelength. When we solve for the lambda m, for m equals to 0, we have the original relation. For m equals to 1, the original center wavelength is divided by 3. For m equals 2, the original center wavelength is divided by 5, and so on. Therefore, when our center wavelength is set at lambda equals 0, we have the reflection band. And also the same band is emerging at 1/3 of the wavelength, 1/5 of the wavelength, and so on. Let's again take a look at this situation in MATLAB. We have the distributed Bragg reflector consisting of quarter wave thick layer pairs. And we keep the total optical thickness constant to maintain the center wavelength as discussed in the lecture notes. When the parameter A equals 1/2, we have the quarter wave thick layers. The center wavelength in our example is 1.5 micrometers. Layer thicknesses and refractive indices can be set. We can define the substrate index, wavelength range, and number of layer pairs. The refractive index and thickness vectors are formed by repeating the layer pairs using repmat function. And when the number of layer pairs is increasing, the reflectance is increasing. Now we see the original reflection band around 1550 nanometers, and the other band, which is the center wavelength divided by 3, so we are at 520 nanometers. There would be even more reflection bands at the shorter wavelengths, which are the original center wavelength divided by 5, and so on. If we deviate from the quarter wave thickness condition by changing A, we see that the position of the original bands is not changing, but we have an additional reflection band at half the original wavelength. And this is a consequence of the deviation from the quarter wave thick layer thicknesses. In addition to the reflection, we need to take the dispersion of the mirrors into account in some cases. And let's review how this is done. Reflection of the mirror can be separated in magnitude and phase. Both can be calculated from reflection coefficient of the field of the mirror. Group delay is the derivative of the phase with respect to the angular frequency, and the derivative of the angular frequency can be converted. Once the group delay is calculated, we can calculate the dispersion parameter as a derivative with respect to the wavelength. This is realized in MATLAB by calculating the phase from the reflection coefficient by the angle function, and we'll see that the phase corresponding with the reflectance has a lot of phase jumps. These can be eliminated by the unwrap function, and we have a smooth phase response corresponding with the reflectance P. The group delay is the derivative of the phase, and we see that it's flat around the center wavelength, but it's increasing towards the edges of the reflection band. And dispersion is calculated as the derivative of the group delay, and we'll see that it's also increasing towards the edges of the reflection band. The values of the group delay and the dispersion are small, but they still might have significant effect in optical systems, especially for ultra-fast pulses.